Good morning and welcome back. In this section, section 4, we're looking at linear motion and the area under a curve, which really should be called linear motion and the area under a curve revisited, because we've done this before. We're just going to have different looks at it. And sometimes, like, we've done a lot of linear motion where we're given the distance or position function, we've found velocity and acceleration. But now, being able to take the antiderivative or the direct integral, we can go backwards. Given a velocity or even acceleration function, we can find the distance or position of the particle. They're generally particles. It's a very generic, bland type, but it could be expanded to anything. It could be your car. It could be whatever. Particles just can go backwards and forwards a lot easier along one track. It just simplifies the problem. So let's look to see what we're doing. For linear motion, if we have a velocity equation, here we have the graph. We'll get the equation here in just a minute. There's two things that we're going to have to find. We're going to find the antiderivatives. Now, if we found the antiderivative of this, say from 0 to 100, which is what it'll ask for, we are not going to get a particularly large number because we're going to have this area and this area, but then we're going to subtract these two areas. And so that's going to make it the number a bit smaller. And what that is that's the displacement. So we went to the right, and then went back to the left, and then went to the right, and then went back to the left a little bit. Where did we end up? How far away from our starting point did we end up? That's the displacement. And that's one of the things we'll be finding. And that's pretty easy. It's just the antiderivative of the velocity function from a to b, in this case, 0 to 100. But sometimes we don't want to know the displacement. We want to know how far something actually moved. The displacement is not what I care about in my car when I need to get my oil changed, because the displacement is going to be basically 0 because I end up at the same place every night. So every day my displacement is 0. But my oil is still getting used. My engine's still getting wear and tear. So finding the overall distance is also important. And to find the overall distance, what we do is we take the absolute value. Well, there's a couple ways. We take the absolute value of each thing. So we can find these points where the velocity is 0. That's where it's going to change. And we would take the antiderivatives of each of those separately, the definite integral. The antiderivative will be the same for each. The definite integral will be different. And then we just make the ones negative positive. This one, go. There we go. And then we'd add up a bunch of positive values. And that would get the distance traveled. Another way of doing it is by simply taking the absolute value inside of the integral, the absolute value of the velocity equation. That doesn't really work if you're finding it by hand, but most of these, in fact, most of what we're doing today in general is going to be using your calculator and using the numeric integration on your calculator. It's very rarely today are we going to actually have something that we can integrate by hand. Most of them are going to be things that are beyond that capability, but that's why we have the tools that can help us do it. And these particular things would be on the calculator allowed section of the test. So, linear motion, we have the displacement. That's just how far is the change from beginning to end. And that's just the antiderivative from a to b of the velocity. And again, that might be you go all the way to the south on the island, then come back and you park in the parking spot next to you. Your displacement is like 3 feet. Now for the distance to get all the way to the south end of the island and back, we would take the absolute value. Now notice the absolute value is in here. It's not on the outside. That would be bad. We don't want the absolute value on the outside. The absolute value on the outside would just give you the displacement, but positive. It is possible for the displacement to be negative if we ended up to the left of where we started. It is not possible for the distance to be negative. The distance will always be positive, and in general it will not be 0 because that is no distance. There's no movement there. That wouldn't be, like, nothing happened. There's no reason for the distance to be 0. But the distance will always be positive. The displacement can be either, and the distance will always be greater than or equal to the displacement. If you just drive straight in one direction, your distance and displacement are the same. But as soon as you turn and start coming back, your displacement is going to go down and your distance is going to keep going up. So that will always be bigger. So let's look at our graph over here. Let's erase some of my doodlings. There we go. And then if we look at this equation, the problem that goes with this is a particle moves along the x-axis such that its velocity at time t is greater than 0 is given by v of t equals sine of the square root of t for 0 is less than or equal to t is less than or equal to 100. The graph of v of t is shown. That's what we're just looking at. So this is sine of the square root of t. Find the displacement of the particle from time t equals 0 until t equals 100, and then find the distance of the particle. The particle moves from time t equals 0 until time t equals 100. Most of these questions are going to have you find both. Part of it is to the practice of finding both, but part of it's also just to see the difference between the two. So for the displacement, we just have the antiderivative. Sine of the square root of t, people think, well, that's just going to be negative cosine the square root of t, but no, the t, there's chain rule in there. It gets really messed up. If it was just sine of t, then yeah, it would be negative cosine t. But with that square root, weird things happen. So we plug it into our calculator in the numeric integration, 0 to 100, and we get the displacement is 15.6934 units. In this case, it doesn't give us units. If it does, put the units in, include the units. And then the distance, same thing, except we have our absolute values. And you can put it into the calculator directly like this. You don't even need to find the points where it intersects. And you get that the distance is 59.7048 units. So notice the distance is a lot more because the displacement, this first section we get some positive, but now we get more negative. If we found the displacement at that point, it would be negative. And then we get a bunch more positive to put us positive, and then just a little bit more negative to keep us but we're staying positive. We have more area above the line than we do below the line, so we'll still be positive. So that's linear motion. How the problems that we'll be looking at today are a little bit different than what we've seen in the past. But even still, this relationship between distance, velocity, and acceleration is such a fundamental relationship in calculus in general, specifically first year calculus. It's a huge idea. And so hitting it again can only help. The next topic we're looking at is the area under a curve. Now, we just got done with a bunch of this at the beginning of the last chapter, and we did it a little bit before. The difference here is that the area under the curve won't be described by an equation. It'll be described by a graph. And a lot of times this will be a velocity graph, and it'll ask you to find the distance. Or sometimes it'll just say f of x equals the antiderivative of this graph. Kind of like a graph of f is made up of lines and a semicircle is shown. So that just says that what it looks like, it actually is. Like, it's not trying to trick you. Let capital F of x equal the integral from -1 to x of f of t dt. So the first thing to notice is it has a starting point there. This is huge because people like to start at the axis. In this case, we're starting here. This is where everything's going to come from. And so it's important to do that. I always draw a line there just so that I can see where it is to remind myself, so I don't accidentally do something horrible and start at the axis or at x equals 1 or something like that. And so now we need to find f of 5, f of -5, and then f prime of 0 and f double prime of 0. So these first two, f of 5 and f of -5, are going to be the area under the curve because that's the antiderivative. To find the areas under the curve here, we're going to use geometry. That's what we're going to do. It's not a calculus problem so much. This is actually using the fundamental theorem of calculus, but how to find the area is geometry. So if we want to first start by finding this red triangle, the triangle area is going to be 1/2 base, we went over 2, times height, we went up 4. So that area is going to equal 4. We can find the semicircle area. So this area, the area of a circle is pi r squared. So semicircle is going to be 1/2 pi r squared. The radius is 2. So we have 2 squared is 4, times 1/2 is 2. So we have 2 pi. So that's those two. Those are the two pieces that make up this f of 5. f of 5 is going to be the area under the curve from -1 to 5. And so we're just going to add these two pieces together. But we're not going to add because this is below the curve. That's actually a -2 pi. So f of 5 will be 4 minus 2 pi, which we can leave at that. Later on, we will figure out what the approximation is because we'll need it for a different part of the problem. But right now, we can leave it there. So knowing that it's negative is important. Now, for f of -5, going backwards is kind of weird because everything's going to switch signs. The stuff above the curve is actually going to be negative. The stuff below the curve is going to be positive. One way to think of it is this first little rectangle here. The height is 4 and the width is -1 because we're moving backwards 1. So here this area is going to be -1 times 4 is -4. And then we're going to have this triangle. It's going to be 1/2 the base of -1 times the height of 4, which is -2. And then we'll have this triangle, which, we'll put it here, we have 1/2 and then we went backwards 2, and then we went down 4. So we have 2 negatives there, which make that a positive. And so to find f of -5, we're going to add those 3 numbers together. So now getting the negatives backwards is one of the biggest mistakes people make on this type of problem. But here we have -4 minus 2 plus 4. Which equals -2. So we started at 0, we went backwards 6, and then forwards 4. So that's those two. The other two are remarkably easy to find. F prime of 0. So F prime, I'm going to erase some of my little shapes here so we can see the graph again. Now F prime is the derivative. It's the slope. The slope of capital F is the lowercase f. It's what we're looking at on the graph. The graph is the slope. So f of 0 is 2, or f prime of 0 is 2. It's the y value on the graph. Remembering this relationship and what to look for here is the hardest part of this problem. So f prime of 0 is 2 because that's the y value of the graph, which means f double prime of 0, the second derivative, is the slope of the derivative, so it's the slope of the graph. This is just a straight line. So the slope of this line, we're going to go down 4 over 2. That would be -4/2, or -2. And so that is how you can find those pieces for part A. Part B uses this stuff. Actually, we've actually found most of what we need here, especially since we have all of those pieces. So find the absolute minimum and absolute maximum values of f on the closed interval. So if we remember, these absolute maximum, absolute minimum values can happen at a couple different places. They can happen when the derivative changes signs. So that would be there and there. Or it could happen at the endpoints of the interval, since it's a closed interval. There. So we just have to figure out what f is at those values and then pick which one's the biggest, which one's the smallest. So we already know 2 of them. Let's put them in order here. F of -5, f of -3, f of 1, and f of 5. So we know f of 5 is 4 minus 2 pi. We know f of -5 is -2. F of -3 is just these two added up, so the blue and the yellow, that would be -6. F of 1 is just this initial triangle, the red one up here, so that would be 4. And so we need to figure out which is the biggest, which is the smallest. So here, f of 5 is 4 minus 2 pi. Not really helping us. 2 pi is about 6.28. So 4 minus that is going to equal about -2.28, which all we need to know about that is it's not the smallest, it's not the biggest. What we have is f of -3 is the min, and f of 1 is the maximum, because those are the absolute values, or the highest and the lowest values that we have. And so that's part B, finding the absolute minimum and absolute maximum. Part C and D, for what values of x in the open interval is f increasing? So remember, f is the antiderivative. For it to be increasing, we need the derivative to be positive. The derivative is the graph that we are looking at. Where is this graph positive? It's positive when it's above the axis, so it'll be positive there. So it is increasing on the interval -3, 1. You could also write it increasing when -3 is less than x is less than 1. It's another way of writing it. We don't want or equal to here, because at those points it's neither increasing nor decreasing. But you're just looking for when the actual graph values are positive. And now down to when is it concave down? So the concavity, the second derivative, is the derivative of the derivative. It's the slope of the derivative. It's the slope of the graph that we're looking at. Concave down means we need a negative slope. So where does it have a negative slope? It has a negative slope from there to there. Otherwise, here it's positive, then 0, and then at the end it's positive. Has a negative slope from -1 to 3. So it's concave down on -1 to 3, which you could also write, or it's concave down when -1 is less than x is less than 3. Again, we don't have an or equal to, because at those points it's inflection points where it's neither concave up nor concave down. And so those last few are super easy. Most of the work in this problem happens right there. That one is done by observation. F prime of 0, all right, we had to find a slope. Y minus y over x minus x. Part B, we already had the work done for it. We just needed to know what to do with it. Part C and D are done by observation. We look at it, it's like, oh, hey, this is where the graph is greater than 0. Hey, this is where the graph is negative, like the slope is negative, it's going down. So we can look at the graph and see those values. The important thing is you need to know what you're looking for. So again, it's that the graph is the derivative idea that we need to think about there. And so that's the second piece. Third piece, we're going to see some more differential equations in this section. And I use the term differential equations loosely because they're just more, it's an equation, but it's an equation of the derivative. So something like this, dv over dt equals this, which has only t in it. So you would just multiply over, you're going to find the antiderivative. There's nothing funny, no separating the variables and solving like we were doing. It's just technically, this is a differential equation because it's the derivative equals something. And we're going to have to answer questions about this. A lot of times, it's going to have us finding the antiderivative or the definite integral between two values. In this case, we have the rate at which ice is melting in a pond is given by dv over dt equals the square root of a whole bunch of stuff that we are not going to find the antiderivative of this by hand. Remember when I said that most of what we're doing is going to use a calculator today? That includes this. Where V is the volume of ice in cubic feet and T is time in minutes, what amount of ice is melted in the first 4 minutes? So we're going to find the antiderivative from 0 to 4. because we want to know the amount of ice in the first 4 minutes. If this is the rate at which it's melting, the antiderivative is the amount that it's melted. And so we'd set it up. I multiplied t over. You really don't have to. But antiderivatives from 0 to 4, again, this is not something that I would expect you to be able to do by hand. So we plug it into our calculator, we get v equals 5.84849. That is great work. That, however, is not an answer. An answer to a question like this, where it gives us context, it gives us something. We are solving a problem. That answer needs to be in context. And what I mean by context is it needs to include a unit, because I can almost guarantee you a question like this, the unit will be given. So it needs to include a unit, and by reading the answer, I should know what the question was asking. And so it's not just 5.84849, it's 5.84849 cubic feet of ice have melted in the first 4 minutes. So that is what an answer to something like this looks like. This would probably be a 2-3 point question on the AP test. This might get you 1 point. The other pieces are going to be in how you answer the question. I mean, this is good. Like, we need this as part of our work, not an answer. Some of the questions that you'll get will actually just ask, what are the units? What does it represent? Like, so you don't have to do any math. You just have to know, what are the units? What does it represent? And so you'll have that. You have these, which again, the math is done in your calculator. We are practicing this a bit. But then you also have the interpretation and the practice of writing it appropriately. You have the area under a curve, given a graph, and you have the distance problems, where you have to find the distance and displacement. So that's what we're working on today, and probably tomorrow as well. And so, while you're working, keep working problems, keep asking questions, and as always, happy mathing.